So yesterday I was at the Cambridge Maths Open Day, and if you went to go see the maths faculty at the maths department just near Churchill, they'll have given you some sheets. There was a tent outside, and they were handing out, I think, 4 or 5 sheets, maybe four. And they had 7 questions on them. These were more like puzzle type questions, and I wanted to go through them. They also did hand out some practice step questions, but they're all available online, so I'm not going to go through them. Um, but I'll go through these ones. Okay. Um, I There's a question at the end which is the only one that I couldn't get, and to be honest, I'm not fully sure how to explain it. So my explanation will be a bit wishy-washy for that. So hopefully somebody else can write a better one in the comments maybe. Anyway, so like the sheets, they follow as like an adventure, and along the way you're meeting knights, elves, goblins, dragons, things like that. And there's some context to it, but I've not written the context because it's not really necessary. I mean, it's nice, but it takes a while to write up, so I've not included it. But the first question is, it starts you off easy. It says, "It is now summer. Which of the 4 seasons will it be in 1,646 seasons from now?" Right. So the way I did this question is I said, well, the seasons repeat every 4 seasons, right? So if I am in summer and I go forward 4 seasons, I will also be in summer. Well, this number here is not exactly a multiple of 4, right? If you divided this number by 4, you'll get a remainder 2, right? So 4 goes into this some amount of times, and then you get 2 left over, right? So it goes into it 411 times, basically, right? So up here, just up to this, so 4 times by 411, right? This many seasons from now gets me to summer, right? Because it repeats every 4, right? But I also have a plus 2, right? Because the number here isn't 1,644, it's 1,646, right? So I have to go forwards an extra 2 seasons, which means I go through autumn and into winter. So the season I'm in must be winter. The next question. So what we do is we take a number, we add the digits, and if the result is less than 10, we stop. Otherwise, we repeat step here with the result. And the proposition is if the final result is 9, the original number is divisible by 9. Otherwise, the final result will be the remainder of the original number on division by 9. Right, so the way that I did this question is I said, okay, well, okay, the question is here, sorry. Is a proposition always true? Can you prove it or find a counterexample? Um, First of all, I just wanted to say I think this is true because the divisibility test for 9 is just summing up all of the digits and then checking that they're divisible by 9, and if they are, then the original number is divisible by 9. Right, so I already have a feeling that this proposition is true, but let's try and prove it. So what I did first of all was I considered a simpler case, right? So I considered, imagine we had a 3-digit number, and any number, no matter how many digits it is written in this form more or less, right? You have some amount of ones, you have some amount of tens, and you have some amount of hundreds. So for example, the number 573, well, that's 5 times by 100 plus 7 times by 10 plus 3. Right, so any number can be written like this. And what we're saying is that the sum of the digits, okay, well, that's just going to be a1 plus a2 plus a3. If that is 9, then the original number is divisible by 9. So let's say it is 9. Okay, well, if it is, I'm just going to go ahead and rearrange for a1, which is this. Okay, and if I plug this back into here, I've just put brackets around it, so it's simpler. Well, 10a2 take away a2 is just going to be 9a2. 100a3 take away a3 is going to be 99a3. And we get this, right? And we can factor out a 9, and this is a multiple of 9, so therefore it is true. But that's only for 3-digit numbers. It's only the first part that we've actually proved. We've still got this otherwise that we'll look at later. Right, so it's true for 3-digit numbers. Now let's try and take this idea and use it in a more general case. Okay. Also, with these types of questions, I've always found it easier to split up the number like this. It's kind of like a method that I realized worked for a couple of problems, and I've decided to kind of add it to my tool belt. So this is most of the time this is what I do if I'm trying to answer a question like this, right? Okay, so we can write all of the number like this. Okay, so some amount of ones plus some amount of tens plus some amount of hundreds, etc. Everything in between, all the way up to the last one, right? And just be careful, the power of 10 at the end is going to be n minus 1, not n, right? If you notice here, this is 10 to the 0 to get you 1, a1. This is 10 to the 1, 10 to the 2. So the power of 10 is always 1 less than this subscript number here. So this is 10 to the power of n minus 1 times an. Okay, well, if we sum all the digits and they equal 9, then this original number must be divisible by 9. So let's go ahead and rearrange for a1. Right, so we're going to subtract this, subtract everything in between, and subtract the last one to get this, and we'll plug that in there. And then here we're going to reduce this by 1. We're going to reduce this by 1, and everything in between we're going to reduce it all by 1, all the way up to the last one. Right, this number here, let me say, it's a power of 10, and then you're subtracting 1 from it. Any power of 10 subtract 1 is a multiple of 9. Okay, yeah, so this here, it must be a multiple of 9. And because these are all multiples of 9, then the entire number is just a multiple of 9. So the first part is actually true. Now, in regards to the second part, where we're on about it being a remainder, well, we can use more or less the same idea, right? But instead of having a 9, we're going to have a 9 plus some remainder, right? So what we're saying by having this 9 here is our number here is some multiple of 9 plus some extra remainder, right? Hopefully that makes sense. Any number can be written as some amount of 9 plus some remainder, so even if that number isn't a multiple of 9. So for example 82, well, that's 9 lots of 9 plus 1, where 1 is the remainder. Okay, hopefully that makes sense. And say for example 4, that's going to be 1 lot of 9 and the remainder is going to be minus 5. Okay, so this r here can be positive or negative. Maybe it's not the best idea to kind of use it in less than 10, for less than 10, but it's fine. I'm sure you get the idea. You wouldn't be using this this recursive technique if the number was less than 10 anyways, so that kind of prevents r from being negative. Anyways, so let's just go ahead and rearrange for a1 again. We'll get this, but we have an r here now. I've just copy and pasted this. We have an r here, and then the r is still there. We still subtracted 1 from all of these, and this entire number here is a multiple of 9, right? But we have some remainder at the end, right? So we have a multiple of 9 plus a remainder, right? So the final result, right, will just be the remainder. Okay, because we're essentially going to reduce this 9 into like nothing. Okay, and then we'll just be left with the remainder. So the second part is also true. Okay, so the full proposition is true. Question 3, so we have goblins who always lie and elves who only tell the truth. And one of them says, the first creature says, one of us is a goblin and the other one an elf. And the second one says, that is not true. Which type is each? So the way that I do these types of questions is just, I assume one of them is telling the truth and one of them's lying. Okay, I'll just assume that the first one is telling the truth. Okay, so let's say this one's telling the truth, i.e. he's an elf. If he is an elf, right, he's this sentence here, we can take it as factual. He's saying one of us is a goblin and the other an elf, right? That elf must just be him. He must be talking about himself, right? So he's telling us that this second person is a goblin. So this person, whatever he's saying, he must be lying, right? So that person is saying that is not true, but this is a lie, which means that this is true. Okay, well, this is true. This makes sense. He's only reinforcing what this person said, right? Which makes sense because he's a liar, because he said the opposite. Okay, so this is actually true. And maybe this was the more difficult case to actually consider first. So instead, I've included this one. Let's instead assume that the first one is a goblin. Well, if the first one's a goblin, okay, then he must be lying about whatever this sentence is. He's saying one of us is a goblin and the other an elf. Right, well, one of us is a goblin. That's correct. He's the goblin, which must mean that the second part is incorrect, right? Because he's a liar. He doesn't tell the truth. So he's lying about the second part and the other an elf, which means that he's saying that the second one must be a goblin as well. Okay, well, if this person's a goblin, then he's lying about this, right? So in fact, what he's trying to say, the second person, is this is true. Well, if this is true, which it's not, because the first one is a liar, then that's just a contradiction, right? There's a contradiction here, because this here can't be true, which is what this person is saying, and this person is saying that this guy's lying, right? So he's saying that he's lying, he's saying that he's telling and he's saying that he's I don't know, it just got stuck in my head. Hopefully that explanation made sense. I'm not going to think about that for any longer. But this here, the second one, is a contradiction, so this one is false. And if you wanted to consider this one first, then the only other thing that the first one could be is an elf. So the first one must be an elf, and the second one must therefore be a goblin. Okay, question 4. So still goblins telling lies and elves telling the truth. They're in court now, and the judge asks a witness, "What type are you?" and the defendant, and the witness replies, "The defendant and I are both goblins." The defendant shouts, "I'm innocent." Is the defendant guilty or innocent? What type is the defendant, and what type is the witness? Right, I've just not animated this at all, apologies for that. Let's first of all assume that the witness is an elf, right? So I just start by assuming that the first one's an elf. So if he's an elf, then he's telling the truth about whatever this is. So he's saying, the defendant and I are both goblins, so this is true, right? But hold on, that can't be true, because we've assumed he's an elf, so he's already contradicted himself. Therefore, that must be incorrect, so he can't be an elf, because he just contradicted himself. Therefore, he must be a goblin, and the defendant is an elf, and he's innocent, because he's telling the truth about him being innocent. Question 5, we have a 10 by 10 chessboard, and we're basically stacking 5 pebbles on each square, and each of the pebbles can either be red, blue, or white, right? But order, you have to consider different orders as different cases, right? So blue, blue, white, red is different from red, white, blue, blue. And we have to make a bet with I think it's like some ogre, that there will be at least 2 squares with the same pattern, or that there will not be 2 squares with the same pattern of pebbles. What should you bet, and what are the chances you will be correct? Well, let's just consider a single square, right? Say we're stacking these 4 pebbles on top of each other. Well, the first pebble, there's 3 different colors it could be. It could either be red, blue, or white, right? So there's 3 different options for the first one. And for the next one, there's still 3 different options. It could still be red, blue, or white. And for the next one, it could be red, blue, or white. And for the next one, it could be red, blue, or white. Right? So the number of permutations, careful, permutations, not combinations, that's kind of just like semantics. If they mean the same thing to you, then maybe have a look at the difference between permutations and combinations. So yeah, so there's the number of permutations here is 3 times 3 times 3 times 3, so that means there's 81 like different arrangements for a single square. Okay, hopefully that makes sense. Now, if there's 81 different arrangements, let's imagine that the first arrangement is red, 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 right? And let's imagine the second arrangement is blue, 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 and the next one is white, 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 red, and then white, 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 blue, and then third, fourth, fifth, right? So each arrangement here represents a unique arrangement. Okay, but that means if there's 100 squares, because it's 10 by 10 chessboard, right? When we get to the 81st square, we'll have used up all possible unique arrangements, right? And by the 82nd square, we'll have to have repeated at least one of them. By the 82nd, we must have repeated at least 2. By the 83rd, at least 3, right? So after the 81st square, we've already used up all of the possible permutations, right? So whatever we're placing next, whatever arrangements we're placing on the next 19 squares must all just be a repeat of one of the other squares. Therefore, I should always bet this, right? Because the number of permutations is less than the number of squares. So we can bet it, and we'll have a 100% chance of being correct, because after the 81st one, we are guaranteed to repeat another one, and then after the 82nd, we're guaranteed to repeat at least 2. Okay, that's fine. Question 6. So we have infinitely many red roses and infinitely many blue roses and infinitely many baskets. We place a red rose in each basket. Sorry, a basket, not bucket. I think I've actually carried on this question, assuming it's buckets, not baskets. Is there a way of rearranging red roses to accommodate the blue ones? Is the infinite number of baskets the same size as the two infinities of roses? Right. So let's just have like a bunch of different like baskets down. Okay, this goes on forever. And what we're saying is that, okay, let's say there's red one there, red, 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 all the way up to infinity. There's, we filled it up, each basket with a red rose. Okay, well, is there a way to accommodate the blue ones? Well, let's just imagine for each red rose, we like, imagine we took the entire infinity and split it in half. Right, and we only put the red roses on the even numbers, so either a 2 or a 4 or a 6 or an 8, like this, right? And we can do this because we have infinitely many baskets, right? Even though we have infinitely many roses, well, we're still going to have infinitely many baskets, right? We'll still be able to have red roses in baskets, even if we skip one in between, because there's still an infinite amount, which means that in between the red roses we can actually just put blue ones. So we could put a blue here, a blue here, a blue here, and that means for each odd position we can put a blue rose, and then for each even position we can put a red rose. So yeah, we can accommodate for the blue ones as well, and they are the same size even though they're three different infinities. Okay, sorry, not three different infinities, three of the same infinities. Okay. I think the issue with this is people considering it as finite, an issue which is which can kind of give you the wrong answer on the next question, as we will see here. So the follow-up is the stalks of roses in each basket need to be cut. You're asked to cut each stalk to a length between 1 and 2 inches. Each basket must contain a different rose length, and each possible length between 1 and 2 inches must be achieved. Right? Is this possible? Are the two infinities the number of baskets? Are the two infinities, which are the number of baskets and the number of possible lengths between 1 and 2, the same? Right, so let's go back to our case. So we have this arrangement of blue and red roses. Let's say that the blue rose, imagine we cut that to 1.000000 up to infinity. Imagine it's kind of hard to like write down, but imagine we just have exactly 1.0000 all the way into infinity. And let's say that the red rose, the one in the second position, imagine we have that as 1.00000 going for infinity and then having a 1 at the end, right? So we've actually got more than infinity because we've got infinite places between this, and then we have plus 1. So we have more than infinity here, actually. Okay, well, that's an issue. We've just got more than infinity. Well, more than infinity is infinity, is it not? Right, let's say we carry this on, okay? But because lengths are continuous, right, you'll never actually get an exact length. If you've done, say, the normal distribution, you'll be familiar with continuous distributions, and you'll know that, say, the probability of getting, say, somebody with a height of somebody whose height is exactly 5'10" or exactly 170 centimeters is going to be incredibly low, right? You say it's 0 because it's such a small like percentage that it's just negligible, right? Because where are you going to find somebody with exactly that height, right? You're probably not going to, right? So because the lengths are continuous, you can't actually you can't really describe numbers like this, right? We've got more than infinities within infinities, and that's an issue, right? Because the two infinities must therefore be different, right? So we can't even actually count all the possible lengths, right? So we could never actually cut all of the stalks different lengths. Okay, hopefully that makes sense. Yeah, so the two infinities are different, right? This is the final question. I've gotten all questions correct up to now, I think. I'm not really checked them. And this question is the one which I could not get. I tried to search it up and I couldn't find a good explanation. So I kind of found something from 3 Blue 1 Brown. These pictures are from 3 Blue 1 Brown. It's his video called How to Lie with Visual Proofs or something like that. But anyways, so the question says, right, what we do is we're basically putting a square around a circle of radius 1. Okay, and well, if this is 1 here, then this here must be 1, right? So this entire length across is 2. This entire length across is 2. And because this one here must also be 1, because it's the radius, and this is also 1, then this is also 2. So you have 2 here and 2 here, i.e. 2 here, 2 here, 2 here, 2 here. So the perimeter of this square is 4. Right? And let's say we take this, like, these squares here, so these edges, and let's say we just bend them down to here, and we bend that one down to here, we bend this one down to here, that one down to here, and we repeat this for all sides, for these 4 corners. Okay, well, the perimeter is still going to be 4, right? Because it's the same length. We've not removed any length, we've not added any length. Okay, and we're going to repeat this process for infinity. So essentially what's happening is this, like, polygon, right? It's not exactly a square now. This polygon is basically hugging the circle, and it's wrapping itself around it such that every point like conforms to the shape of the circle. So we basically turned that object of perimeter 4 around the subject, around the circle, sorry, not subject, right? So it's saying, okay, well, if we're basically hugging the circle, right, we're repeating this to infinity, so it's the limit, as we do this infinitely many times, then all of the points do in fact actually just hug the circle, right? And it's saying, okay, well, that means that the circumference of the circle must therefore be 4, because at each point it's always this polygon always has a perimeter of 4. Okay, so if it always has a perimeter of 4, then the circle circumference here must be 4. But the circle circumference is what it's. The circumference is pi times diameter. The diameter is 2. So that means the circumference must be 2 pi. Okay, so it's basically saying that 2 pi equals 4. I think the actual question in the Cambridge sheet was it used a different radius, I think. I think they gave you the full diameter as 1 instead of just the radius as 1. I've just taken these pictures from 3 Blue 1 Brown, and he's used the radius as 1, but it's fine, right? In the Cambridge question, you're supposed to prove that pi equal the proof shows that pi equals 4, but in this case, it's just going to show that pi equals 2. But pi can't equal 2, nor can it equal 4, right? Because it's an irrational number, and these numbers 4 and 2 are rational. So there's an issue there, right? And obviously we know this is not true. So where is the error in this proof that pi equals 4, or in this case pi equals 2 actually? Well, what I found online is that it said that as we repeat this process, as we take the limit, right, as we repeat this process onto infinity, just because the points hug the circle, it doesn't mean the lengths conform perfectly around the circle, right? So the limit, as we repeat this process, is different from the limit of the lengths as we repeat this process infinitely many times. Now, I know that's very underexplained, and it's because I don't even understand it myself, so perhaps somebody could actually explain it a bit better in the comments. Anyways, thank you for watching. Those are all 7 questions, or 6, because I didn't even really answer this one. Thank you for watching.